Let's see. We have Ollie Crabtree, who's logged on first, and then James, the astrophotographer, and Martin Eastburn. 4 minutes to see the mini worlds. Yeah. Aaron Thompson says, good afternoon and a welcome Friday. Andrew Corkill is watching. And we've got more from Ollie Crabtree. Mike Wiesner says it's Friday in this part of the universe. This part of the universe, too.
once they're hydrated with water. Microbial life dominate all sorts of extreme environments. The current world champion for upper temperatures for life on our planet is a strain of archaea, found in a hydrothermal vent. It's known as strain 121. Any idea why it was called that? Maybe you already guessed. It is able to survive and even reproduce at 121 degrees Celsius. And it's this sort of life, which we call extremophile life, that astrobiologists are interested in to support theories of panspermia, where microorganisms might have needed to survive long trips around our galaxy on comets or asteroids to go and bring life to planetary bodies, perhaps including our very own home planet. In the same way that life is transferred around different habitats on planet Earth, you might like to consider that space can also act as one big system, and life is a part of it. And in some ways, that's very true. Have you ever seen a shooting star? Meteor showers are common and can be observed from many parts of the world. We already know that there has been, and still is, an exchange of materials between Earth and Mars, because we have evidence from Martian meteorites that landed here. Space is such an active place, so it's quite possible that some life forms hitched a ride from one planet to another. The difficulty is that such a ride would be impossible for you or me because of the extreme conditions. That's why astrobiologists are studying many types of microscopic extremophiles to test out their limits and to see if maybe life was imported here from somewhere else in space. If we're planning on exploring other planets or icy moons that we think may contain or once contained life, then how do we make sure that we don't contaminate it? It's a very important thing to consider. The Committee on Space Research, COSPAR, has formulated a planetary protection policy to define different destinations in space and allocate them with appropriate levels of protection. For example, the Sun is in a category which says it's not of interest for life detection missions. So we don't have to put in special measures to make sure that we're not going to contaminate it. But it's a different story for Mars or other planets we think might harbour life. ESA has adopted this policy and acts on behalf of its member states to ensure that the requirements are met for all missions the agency is flying to or contributing to, by employing the use of clean rooms for our spacecraft and following strict sterilisation protocols. We can minimise the risk of contaminating other places and explore space in a considered way.
Well, hello everybody, this is Scott Roberts, and hopefully my volume is good, and I was trying on some Bluetooth headphones to see if that would actually somehow work out okay, but apparently that did not work out okay. So we're back to my basic system that I have, and excited to share some stuff with you today about microscopes. So as I mentioned in the last program, I've been confessing all along that this is kind of a new journey for me to learn about microscopy. We have some great microscopes here with our Bresser line, and so it's high time that I dive into it, because as a boy I did have a toy microscope and enjoyed it, but I didn't look at live specimens so much. I had like the static specimens that were already prepared for me. Let's see who all's with us today. I think I mentioned earlier that Ollie Crabtree was on first. We got James the astrophotographer on, Martin Eastburn's here, Aaron Thompson, Andrew Corkill, Mike Wiesner, Thomas Lambert from Reidsville, North Carolina is with us. Andrew Corkill out there in Southern California. Jeff Wise says hello, fellow micro enthusiast. That's great. Richard Grace says hello, and Wade Prunty's on with us. And who else do we have? I think I've mentioned everybody so far. Beatrice Hines, of course. She says, hello, everyone. Happy Friday. Greetings from Belgium. She said she wasn't feeling so good, but that her favorite program is on, and so thank you, Beatrice. That's very kind. That's very kind. And we're doing okay here, So I had yesterday. I was kind of recovering from my shingles vaccine. I'd gotten the double whammy Shingrix vaccine, and nothing on the first go around. The second go around, I had all the side effects that you could get from it. So I was feeling not so hot myself, but I feel good now, so it's okay. Israel Monteros Villatoro says it's an interesting theory, but I asked the question, how many of you think that life could have gone from one planet to the next? Okay, now we've had pretty much verifiable proof that we got lunar meteorites here on Earth, and we think that we have Martian meteorites here on Earth. So, as there's been impacts, on the rocky surfaces of planets, it's quite possible that stuff would have rained, onto other planets. When I think of how hardy and how almost indestructible some of the viruses are, and how strange they look, and you could kind of go, maybe those are the real aliens. I don't know. Tardigrades, another one that can totally dry out, be desiccated, be exposed to radiation, can survive the vacuum of space even. So, really some amazing stuff out there. And we only, we know life as we know it, and so these are the questions that people are kind of, scientists are starting to open up and think about how else can life exist. And so that's kind of my main interest is being an amateur astronomer. Getting into microscopy is, I want to understand how life itself might evolve in different forms, and you get a little tiny taste of it when you start going into microscopy. And so I wanted to, as I'm teaching myself about microscopes, I started kind of this way with telescopes. I just threw myself out there and started giving presentations about telescopes, astronomy, comets, and just started giving talks. Kind of like how Libby and the Stars is doing it, although I was in my 20s and she's started when she was 10, so that's a little bit different. But I do have a PowerPoint presentation that I can share, and let's see, let's take that, and here we are. And let me bring this up full screen. Here we go. And so this has to do with the invention of the microscope. And it's interesting, kind of like a lot of inventions, you see a lot of people kind of discovering something or making something for the first time. The first optical compound microscopes, and this is the type that I use today, were developed roughly at the same time as the telescope. We could go way back to where people first started making lenses, I guess, back in the maybe the Vikings were actually making some lenses to create fires and stuff like that. But I'm sure that they played with them and figured out that you could see through them. And so when did the first telescope take off and the microscope take off? It's hard to say, but there are people that give credit to Hans and Zacharias Janssen that developed a microscope in 1590. Hans Lippershey, the guy that's credited with developing the telescope, in 1608. Apparently he filed for a patent, so I think Hans liked to file patents. Galileo had a microscope, probably maybe with some slight improvements or something over what Hans Lippershey might have provided for him, so that's another question. I mean, you start reading who invented the microscope and you look at different websites and you're going to see lots of people credited, but these are all the people I've found credited so far. And then there's this guy Cornelis Drebbel in 1621. So one of the things to point out though is that these microscopes are relatively low power, like somewhere between 3 to 10 magnification, something like that. But they did make the job of making small objects look bigger. And so then you get to the people that are documenting their work, okay? And it's kind of like the astronomers. One of the things that we say is if you don't write down your observations, you're viewing, or you're being a tourist of the sky somehow, but you're not making a confirmed observation, and writing it down and documenting it is very important. In astrophotography, it's easier because you're getting lots of data in your TIFF file or whatever. So you had people that were starting to make illustrations and stuff. And this guy, Francesco Statoliti did a work called Aparium, and it was a study of bees in 1625, and he used a microscope. And so this is referred to as like the first illustration of microscopic views. So that must have been very startling in his day to publish this. This dude was also described as someone that was very studious, very quiet, very methodical. And so he had he was slow but sure, so. And then you have a drapery merchant, this guy, Van Leeuwenhoek. Now, when I first started studying microscopes, I thought this guy was the first to invent microscopes, but he's not, Van Leeuwenhoek did his work in the 1700s, late 1600s, and he made his own microscopes, and you can see the illustration here. This thing is about maybe 2 inches long, 2 or 3 inches long, and maybe like half an inch thick, something like that. And the way it worked is these 2 plates would capture a lens, a single lens, that Van Leeuwenhoek made, and then on that little point that you see with the little screw at the very tip there is where he had put the specimen, and so he could adjust the in and out and the up and down, and get his focus, as well as he could, and he would put this device right up to his eye, okay? So the lenses that he made were these little tiny spherical type of lenses, and I'm hoping I've ordered some glass rods and some material so I can melt the glass rods and actually try to duplicate how this guy made lenses, okay, and how he made microscopes. The thing that Van Leeuwenhoek is credited with big time is that he went way beyond the magnification ranges of the compound microscopes that were first made with this simple microscope that went over 200 magnification. He discovered he was a drapery merchant, and he wanted to find the best threads, and so he was going to use a microscope to study it with. And what he finds is these animalcules, I guess is what he called them, but he discovers bacteria, and he finds it on the cloth itself. And so that's very interesting. But this microscope that he made, I think you can make it with like cardboard or something. So I'm actually going to try that at one point. That's going to be fun. Van Leeuwenhoek was then, because he's seeing these tiny organisms, he's the first to really see these things because he's the first to have a telescope this powerful, or a microscope this powerful. He starts making illustrations of what he's seeing. And so he's considered the father of microbiology, and so he laid the foundations for plant anatomy. And also he is the first to see sperm under the microscope. And so he realizes that common held beliefs of things like, how things reproduce, and that what we could just see with our own eyes is the limit to life. Well, it's hardly the limit to life, So Van Leeuwenhoek was not of the same caliber of scientists as some others were. However, his illustrations and his discoveries vaulted him to the highest levels of the scientific world, and his ability to make these super nice lenses, which apparently he kept all the good ones for himself so he could keep making discovery after discovery. When he had visitors, he would show them microscopes of only medium quality, so they weren't that sharp as compared to his own. So there you go. And I'm going to end it there for the slide presentation, and I'm just going to do kind of an ongoing thing as I learn more about microscopes and how they're made and all of that. So let me escape out of here. Here we go. And okay, all right. So earlier today, what I did is I went and found some moss. Okay, and I was watching a video on how to collect specimens. So we have some nice moss right out in front of the Explore Scientific parking lot here. So I gathered up the moss, and what I'm going to do is I'm just going to put some water over the moss itself. Okay? And then what I'm going to do is I'm going to take one of the moss heads, or maybe all of them, and squeeze them out into this bowl. And so in an effort to try to find, maybe I find a tardigrade in there. We'll see. It's kind of messy. Here's another one. It's kind of dirty water. Some good Arkansas mud, I guess. And there's the last one here. Okay. So I got that. Now we're going to take this off. And I'm going to show you guys some microscopy done by Anke Morbitz. Anke works, she's a chemist who's also a microscope expert, and she works at Bresser in Germany. And she has sent me several videos, and I'm going to play this one for you as I set up the other microscope. So here we go. So I'm back with you. This is one of the things I found inside this one of the drops of water here, and I think this is either a microscopic worm or a nematode or something. Again, I'm not so great on identifying this stuff yet, but definitely this is really, really cool. I mean, you're going to find all kinds of little microscopic things just just right in your own backyard, which is totally awesome. Harold says that's amazing, and the symbiosis of life is evident. Yes. Book Davies says it might be a kind of hookworm. Looks about right. Yeah. So let me see if I can find something else in this this drop of water here. I'll move the stage around. Well, that's what it looks like for today. It's just this, just this worm so far. I kind of got skunked on the tardigrades. So, but you get the idea, and it is a lot of. It's just it's a lot of fun to watch them and see what they do over a period of hours. Book says the smallest atoms that have been imaged, I think, were carbon, and those were in larger quantity. It is cool, and I hope, you guys, that I'm able to hook up with someone that does actually have an electron scanning microscope. It'd be totally cool to see something beyond what these optical microscopes can do. But you know, we're observing right now at about 100 magnification, you know, and plus whatever magnification the sensor is giving us here as we are just sampling, you know, just a small portion of the field itself. So, you know, I absolutely cannot see that specimen with the naked eye on that microscope slide. So, anyhow, you guys have a great weekend. We will be back Tuesday, actually Monday and Tuesday, with more programming. We have the Global Star Party that is, I think Cesar Brolo has taken up the challenge to be our special guest host, and so that should be really cool. And we will see you later. And I think that, you know, it looks like some of you too are also getting some great skies, so that's awesome. Looks like it's going to be beautiful here too in Arkansas, so I hope to get out there as well. Take care, and I can't say keep looking up on this program. Maybe I can. Keep looking up and down, okay? So I think you're also going to enjoy this next feature. This is a biologist looking in a cave for specimens, which is also very cool. I'll have to do that because Arkansas is known for its caves. So maybe I can get a scraping or something on the inside of a cave and bring it back. Take care. Thank you. Beatrice says, thank you. Keep looking down for now. Yep. And have fun, you guys. That's the main point. Bye-bye.
One of the important things about looking for samples in a cave is that many of the features are rather subtle, but once you actually learn to see them, you can pick this pattern out as you go through a cave. So I'm standing by an example here which shows a couple of different really important features. One is that there are shiny colonies that are growing on the walls, and these are, in this case, a contrasting color to the wall. So this shows that there are colonies of microorganisms growing in those particular environments. The second feature that we see here is all of these sort of complicated, convoluted maze-like patterns. And those patterns are interesting also because that is a pattern of microbial growth on the wall. So as you travel through a cave, it's important to be aware of these subtle patterns that you see as you move through the passage. One of the important things to prepare yourself as you go through a cave to figure out where to look, where organism colonies may be the most abundant and reachable, is to really think about the geology as you go through and think about the actual shape of the cave. So in places that have sort of low overhangs, like where I'm standing here, very often this is a place where air is compressed as it goes through the cave. And this is a place where moisture condenses out. And many of the organisms are waiting for that moisture to be delivered in order to grow. So these are places where you can actually see them. It's also a place where the organisms tend to precipitate or help to precipitate the presence of minerals that grow on or around them. And so both of those kinds of features often occur together, and so that's one place to look. A second place to look, of course, is where there are bodies of water. So if there are small pools within caves, then you can see sometimes active growth, or you can see in ancient pools and caves. Those would be places to actually look for samples that may have microfossils in them. One of the important indicators of potential microbial growth is color. So many organisms are white when they grow in a cave, but many others have an array of beautiful colors, from yellow, kind of an off-white, gold, orange, red, even blue and green, or purple. And some caves have even a gray, shiny appearance to them. And so, for example, this feature that I'm standing under here has a number of what we call Actinobacterial colonies. And these tiny little colonies have a beautiful golden color in this particular cave. Other caves may have other colors. So what one is really looking for is contrast in color or texture, or a degree of vertical development somehow coming out from the surface of the rock. So texture is another aspect that's really important. These so-called biovermiculations that we see here is an example of a large-scale texture. But some textures are very, very fine. They can be wrinkly, or they can have tiny little prominences that come up in the texture. So really the message is anything that stands out from the background of the cave may be of significance. And those are places where you should stop, you should look, sometimes using a hand lens where you can actually look and see even a slightly magnified version can help you decide whether this is a particular place that you want to sample. I'm taking an ordinary lighter and an ordinary field knife, one of the blades, and burning off any residual microorganisms or organic material that might be on there. This is a rather crude method of taking samples in the field, but it's very effective. Because we're looking for microorganisms that use rather specific and unusual nutrient sources, like metals or other minerals, we are less concerned about contamination than we would be if we were studying bacteria that are more used to high levels of organic material. So I do this a series of 3 times for a number of seconds, because there are some organisms that are quite heat resistant and in a very dormant form called a spore or a cyst. And I want to make sure that I get those guys too, and get everybody off the surface that I'm going to use to actually scrape the sample, or dig the sample, or even sometimes flick the sample off the surface. So one more time to just make sure we've got everybody gone, and then we'll go ahead and we'll take some samples of these actinobacterial colonies and the biovermiculation patterns. Okay. All right, Ilana, if you will, let's see, I'm going to get into position and I'll scrape some material. If you can give me one of these one at a time. And what I will do is put my little finger here, because the inside of this container is sterile, that it has been sterilized. And we want to make sure that only the material we're interested in up on the ceiling here goes actually into the tube. So the usual method for doing this is to clutch it with one hand and then actually unscrew it with the other hand. Keep that clutched in the little finger while you have the knife in the same hand, and then you go towards the sample, and we actually take a small portion of this material. We try to scrape it off. So we've got tiny little crumbs. You usually don't need a lot. And then I'm just dumping that into the sterile container. So I've got a sterile knife, and I've got a sterile container. So that's why I'm trying to harvest this material. Now, if you look at the tip of the knife, you can see that there's quite a bit of brown material on there, or grayish brown material. That is microbial mat and mineral deposit. And the gooey material the bacteria produce called biofilm. So all of that's going into this sample. Now this sample will be prepared, you can barely see it in there, will be prepared for scanning electron microscopy when I get it back to the lab. But the next sample that we're going to take is one to actually grow the organism. So I don't have to re-sterilize right now because I haven't touched this to anything except the surface that I'm examining or want to examine. So I can go ahead and do a second sampling here. And this particular tube has a gel-like material in it, which is used for growing bacteria. And this has a number of different nutrients in it. And we prepare these with different kinds of nutrients so that we can hope to provide the organisms with at least some food that they like. So I'm going to go ahead and lift this up here. And let's see, we've got some of the same kind of material right here. So I'm going to scrape this gooey material here and get as much of it as I can. So I've got a nice big chunk on the end of my knife. And then I'm going to move this back down, and I'm going to insert this into the tube, scrape it off on the edge without touching anything, close it up, and then actually tap the tube until I can get that material down into it. I'm going to give this to Alana so she can hold it, and then hope to bash this material down. Sometimes you have to get really stern with it so that it will go down there. Okay, now you can see that that material that I got is now on this slanted surface of the medium. And so whatever organisms that are contained in that material will immediately think, I'm in a different environment, what will I do? And some of them will like what I've provided as a menu, and some will not. So this is why we use many different kinds of media in order to try to entice somebody to grow on these. And once we do, then of course we can take those back out again and make new cultures in the laboratory. We can work with those organisms, we can test them in many different ways, we can look at them, we can subject them to chemical tests and so forth. So this is really being a zookeeper, going out into nature and trying to capture microorganisms to bring them back so that we can study them. So we are going to take another sample here of this tiny little drop up here that has some golden colonies around it, and it has moisture. And so that's why it's a juicy spot for us to try to capture. I believe that there are actinobacteria in this deposit. And so the medium that I have prepared for this is specifically to try to isolate those kinds of organisms. So this is the one that we're going to use. So here again, I put my little finger on the cap, and I have pre-sterilized my knife. And we're going to go move the whole shebang up there, and then go after that tiny little drop. So I'm actually going to touch the drop to the rim to capture the water. And then I'm going to go in and try to take small particles, put them on the inside of the rim, tap them to go down onto the medium, take another tiny sample here. Even though the amount that we are sampling is very small, it is going to contain a very large number of microorganisms. So the sample does not have to be large. And so I tap it and everybody jumps in there, and then we recap it. And there we are. I'm standing in front of some white material here that you can see on the walls. And this is an interesting kind of microbial deposit because when you first look at it, it doesn't really look like it's the product of life. But what is happening here with this material, which is called moon milk, is that microorganisms living in small fractures within the bedrock are putting out acids as a byproduct of their life processes, and those acids are helping to break down the bedrock. When that mineral material in the bedrock is actually put into a more soluble form, it then starts to precipitate out again, but this time on the filaments and the cell bodies of microorganisms themselves, and even on the biofilm, this gooey material that they make. And so in some places you see fairly thin coatings of this white material. If I were to stick my finger in there, it would actually go in quite a distance because this is very mushy stuff. In some caves we find very active moon milk that's still growing with microorganisms. In some caves we actually have preserved moon milk that preserves the microbial bodies very well. So this is another kind of indicator of microbial activity in caves. Some have very, very tiny thin coatings, and in some places in the world, perhaps there's even a meter deep depth of this material where the bedrock has been altered.